That is odd. Okay. Okay. Today I'm going to go through a couple more aspects of the model that is different assumptions that lead to different, slightly different models. On the last written assignment, I noticed that there were a number who kind of missed one or more pieces of that. And so what I'm going to do is I'm going to record a debrief of that just for those of you who kind of missed that. So I don't want to take class time of it now, but there'll be another. Basically, I'll kind of walk through what all that's about. Okay, but today, and this is particularly the first model I'm going to talk about is kind of teeing up the next written assignment, which kind of combines this with the previous one. So that so today we have a situation, two different aspects of having two different kinds of customers. In the first one, there are just kind of the two different types and the server, and two different types in one server. And when you have a situation like that, then you have to make some additional assumptions about how, which one to serve next. It's, in a way, it's the inverse image of one of the previous models where we had two different servers. We had sort of the fast and the slow servers, and one customer type, but they preferred one server over the other. Here we have one server type and two different types of customers. So that's where that comes up, where the assumption comes up is when in the previous case where there were two different types of customers, two different types of servers. The only place where it really came up was at the arrival. So when a customer arrived, they had to make a choice about which server to go to. But once they made that choice, then everything else was pretty much straightforward. Now, because there are two types of customers, when one type of customer shows up, regardless of which type it is, they only have to check if a server is available because there's only one kind of server. So where does the choice come up? The choice comes up because there's only one server but two kinds of customers. The server, when they finish processing a customer, need to decide which type of customer they're going to serve next. And then in the written assignment, we basically put them both together. So you have two types of customers, two types of servers, and the one type of customer prefers one type of server, but will be served by the other, and vice versa. So that's writ large. And then in the second model today, we're going to kind of look at some of the implications of when you need to have processing by more than one type of server, more than one server. Actually, the servers are still just one type, and and then if there's time permitting, I might do an implementation. I don't have a pre-canned implementation for you. So what I might do is just kind of get one of them started and just kind of show you how to basically do that. Okay, so let's dive in a little bit. So So we have two customer types. There's two arrival types and one server type. And we're going to assume, and like all assumptions, this is something which in a particular situation you would want to examine, see whether or not that's the case. But we're going to assume that the server prefers one type of customer over another. Where this sometimes gets actually implemented in real systems, sometimes have to do with well, in certain types of fabrication shops, you'd have sort of jobs of different sizes, and in fact, sort of people who kind of study how those work. One of the interesting things to come out is if you have a sort of set of jobs, if you don't process them in first come, first serve, but process the shortest job first, then that actually optimizes a certain metrics for you. And by the way, kind of tends to screw over the longer ones, but that's just kind of the way things work. Anyway, so this is a little more abstract than that. So what is it that makes them different? Well, there are two things that are going to make them different, but as far as the server is concerned, the only thing that distinguishes one from the other is the service times. So if I'm serving a type 0, then I need to make sure that the service time delay is say this sequence, and if it's a type 1, I need to make sure it's one of these. And the thing this is where the fact that events can't just sort of make up stuff. Events have to know everything that they're going to be doing. So as we'll see, the event that schedules the delay for a service time of type 0 customer needs to know that that's what they're doing, that in fact is a type 0 customer that they're serving and not something else. There are several different ways of doing that. One way is by having a different event for each one of those. That's one way. Another way, though, is I'm saying that isn't in. Yeah, I can see I do get to it. The other way is that the information can be passed in. So those are the two ways that an event can know about something. It can know about it via one of the variables, via parameter or a state variable. All events know can have access to all of those, or it can be passed in as an argument. Those are the only ways that an event can kind of get information. All right, so let's just sort of take a look at the events for this. So we've defined our state variables. So I need to keep track of how many type 1s do I have in the queue and how many type 0s I have. So type 0, type 1, how many of those in the queue? And that the thing to also understand about how it works in these models, especially in the counter ones, is that there's no necessary relationship between this order and the physical order. In other words, physically, these customers could be doing all kinds of things. The only thing is that I'd be able to identify it. So as far as the model is concerned, we're not representing these physical things yet. This is still all fairly abstract. So picking a state variable, and this is something that picking a state variable, let's say Q0, the number of type 0 customers in the queue, what can cause it to change? Well, an arrival of a type 0 customer. And just as before, this is not a parameter. The name of this event is arrival 0. That's the name. And similarly, what caused it to change? It would go down by 1 if we start service on a customer of type 0. And similarly for type 1s. So here and here, And then this should all look very, well, yeah, I forgot to start with run because I hit it down here. So always start with run. And okay, but now here, okay, so now here's something something kind of interesting, which notice that there's only one end service event. Why? Because now we might have to modify that, but if I choose the state variable S, the number of available servers, what can cause it to change? Well, I could either start service on a customer of type 0 or on a customer of type 1. That causes it to go down by 1. What causes it to go up by 1? Well, when I finish service, but when I finish service, do I need to know which customer I finished service on? And the answer, at least initially, is actually I don't. Why? Because that information is not necessary. Now, it may be that at some, as I'm building, as I'm trying to connect this, especially trying to connect the scheduling edges, it may be that you can't see this, but what this thing is doing is it's, see, it's taking away my mouse. I can't, but I need the mouse to control Zoom, and it, for some reason, it just kind of takes it away. I don't know why. Okay, so in this case, I don't have a need for it. So, all right, so let's start connecting these. This is fairly straightforward. If I have an arrival of type, now, do I need to check the other queue? Okay, these are the preferred ones. These are the unpreferred ones. And I'm claiming that for the unpreferred ones, I only have to check whether there's an available server. Okay, so now, I'm sure at least some of you are thinking, because this is the unpreferred one, do I need to check to make sure that there are none of the preferred ones waiting? Okay, why? Correct. Now, but yeah, I mean, you're absolutely correct, and that's definitely going to come in. However, notice when the lower priority customer shows up and there's an available server, how could it be that there are higher priority customers actually waiting? What is that server doing being idle when there are these guys waiting to be served? But nevertheless, that's something that you should always have that thought in your mind. That's okay, what about the other one? And then just reason it out. Okay, now, and again, here's the thing. So here the delay is going to be the service time for the preferred ones. And now, how does this event know that this is the right one? How does it know not to use the other one? Well, it knows to have the delay for the preferred one because we're starting service on the preferred one. In other words, it's baked into the event itself. This event itself says, if you were to describe it in English, it would be the server begins service on the preferred customer type. And for that type, this is the right delay. So it knows the right delay because it's baked into the event, it's built into the event itself. And similarly here, oops, it knows to do the unpreferred delay because it's built into this. Okay, so now comes the issue. The issue is we now have an available server. We don't want to leave it hanging. So this is where the preference of the type of customer comes in. So if there is a preferred customer waiting, that's all I need to check. So in other words, if there's a type 0 waiting, then 0 waiting, then I want to schedule that. But I may need to schedule this one. But what is the condition? Well, I don't want to do this if there is a type 0 waiting. So one of the conditions for this is that there are none of the preferred ones are waiting. But there are some of the unpreferred ones waiting. That's how I note that. Okay, so in other words, here the preference is represented by the conditions on the scheduling edge, and that's a very typical way to exhibit a quote preference when you have an event which may schedule one or more than one potential other events, but can only schedule one of them. So this is, if you remember a while back, we had, okay, this is what an if statement looks like in event graphs, and that's basically what's going on here. If there are the preferred types waiting, we'll serve them. Else, if there's a unpreferred waiting, we will serve them. That's how we would do code well. Yes.
We have two servers. Type 0 right off the bat. Third type 0 after that. So there's a type 1 waiting queue that hasn't had the start service, but there's nothing. It's the answer.
Yeah. In other words, like as all this is happening, these events are kind of happening. And so these values may be building up, but if we're, and if this is a really good point. The thing to keep in mind for this is that when an event happens and the condition for its scheduling is false, then nothing happens. So in that case, so let's say that I think your example, like we have two servers, and then the first two are the preferred ones, and they grab the server serving them, and then a whole bunch of others start to arrive. Well, as they arrive, each of them checks this condition and it's false. So all that happens is the state transition. All that happens is the state transition. That's important to remember. So that when the first server finishes, then it just checks the state. That's all that happens. So,
Sir, question.
Yes.
I know it's really unlikely, but if an arrival 0 and arrival 1 are scheduled at exactly the same time, how do you resolve that?
That's a great question. You would, well, normally I just kind of say, I wave my hands at continuous random variables. So with continuous random variables, the probability of that is literally 0 and practically, yeah, it's taken away my computer mouse. So I can, anyway, if that were a genuine concern, then what you would do is you would put an even higher priority. So here I put high priorities on start service for that. But if I put a higher priority here, so this is a slightly higher priority than the one here. So let's say they both happen at exactly the same time. Then, well, actually, even without that, if they happen at exactly the same time, that's actually where this high thing comes in. So let's say there's only one server available, and both of these happen at exactly the same time. So whichever one happened to be first, which is kind of arbitrary, the start service event would be scheduled with a high priority, which means it would occur before the other arrival event. So let's say that the high priority one happened to be first. So these are both happening at exactly the same time. But since the event list processes events one at a time, let's say it'll process this one first, and it will schedule a start service with 0 delay and a high priority. That what that high priority does is that puts that event in front of the other arrival event. And so the next event to be processed would be this start service event, which would then take away the server so that when this arrival event occurred and it checks the availability of servers, the server's not available because it's been taken away by this event. And the same is true in reverse order. In other words, let's say for whatever reason, the lower priority one happened to be scheduled at exactly the same time. Well, the same thing's going to happen. It's going to take away the server here so that when the high priority guy shows up, it's not there. Now the thing is that in the model is a little more sort of abstract than sort of the reality. In reality, even if 2 of these guys showed up at exactly the same time, one of them would actually be first. And which one would be first? It's not the, who knows? So does that address the question?
Yes, sir. Thank you.
Okay. I have to do. Well, this won't give me my mouse. And to do here because right, what's happened is whatever this is taken away. I don't have the mouse on my computer. Wait, there it is. Just gave it to me back for just a second. So I'm gonna have to stop this. Let's try. I don't even know how I got it back. I'm just taking it away from that one. Out loud. Anybody have any ideas about how? I know, but it's not. Oh wait, there we go. No. See, what it's doing is it's randomly putting the mouse between my computer, taking away from my computer and putting it here. I was trying to get out of it by ending that. Sorry. See, it wouldn't let me dismiss the pop-up because it was putting the mouse on my computer. And then it was putting the mouse on there, and I couldn't exit Zoom share screen because it didn't have the. This is insane. Okay, so let's try this again here. Now, if I were to, I guess, well, I want the. All right, so now I have the mouse in both places, which is the right. Okay, so did I answer the question? I'll take silence to be consent. All right, so now the issue is something that we've encountered before is that the arrivals events that are kind of kicking this off are now called something different. There's arrival 0 and arrival 1. And so how, what is the second thing that makes one customer type different from the other are their inter-arrival times. So the service times, inter-arrival times. And how can we capture that? Well, that's where these adapters that we talked about yesterday comes in. So if this is an instance of this event graph, and these are two instances of the arrival process, then if we have one that adapts an arrival event to an arrival 0 event, and one that adapts arrival to arrival 1 event, then we'll be able to drive it. And so again, we don't, in terms of implementation, we don't have to implement anything more. When you have new logic, of course, you have to do some work. So this is another illustration of the virtue of laziness, which is don't do work that you don't have to do.
So that's two separate instantiations of the arrival process.
Correct. Yes. Yeah. So the difference between the event graph itself describes the relationship between the events. The events are the state transitions and the scheduling. The listener diagrams are instances. So this would again, and this would directly translate. We would need to decide what the parameters are, but in terms of the structure of the thing, we would instantiate two arrival processes and use it, connect it using adapters as we. Did I do? Yeah, I think I did one for you. Okay. Now the other thing is that when you see a pattern like this, so looking at this, we see the arrival 0 event changes the state of the Q0 event, a state variable, and the start service 0 event changes the state of the Q0. Likewise, arrival 1 changes the state of Q1, start service 1 changes the state of Q1. And so that suggests that what if instead of having separate events for these, we had just one event of the same name, but passed in what type it was doing. In other words, it suggests that we should be able to do something like this. In other words, okay, now this is a different kind of thing, but if you just look at the events here. So instead of having arrival 0 and arrival 1, now I'm going to make that 0 or 1 an index, an argument of the event. And so now, because I passed in which type of customer I've just joined the queue, then I can use that information to increment the correct one. And then when I start service, I need to know which one I've started service on. So if I arrive, regardless of which type I am, this is where that comes in, regardless of which type I am, if I am the right one, and of course we can put our high priority here just to make sure, then I need to say which one I started service on. Why? Because the one is, I need to know which state, is it a 0 or a 1 to change Q? I don't need to know that for S because there's only one S. But I also need to know what the delay is when I finish service. Okay, but now this is where things get a little bit dicey because I had two different conditions. When I finish service, what I do next depends on the state of my system. It depends on if there's the high priorities waiting, then I want to schedule one of those. And since in that condition, I know that it's going to be a 0, so I'm going to actually get past a 0. And likewise, if there are none of those, but some of the low priority ones, then I want to schedule it and pass a 1. So, in other words, in this particular case, that one event can't decide. And you may be tempted to say, well, why don't we just pass I to this end service event so that it knows which one? So in other words, why don't we just pass this? So when I start service here, I know which one I'm doing. Why can't I just pass that to the end service? Well, I mean, I can, but will it help? It won't help. Why? Because the type of customer I just finished on has no bearing on what I do next. If I finished on a high priority one, what I do next depends on whether there's a priority 1 or a priority 0 waiting, and vice versa. So in other words, this gives me no information about what I do next. And so I need to actually kind of deal with it. And of course, now to drive this, I would need the adapter stuff we did before wouldn't work out of the box. Well, it would work, but not with the arrival process. I would need a different kind of arrival process. Let's see, I think we'll get to the right. Okay. So the lesson on argument. Okay, couple of things here. One is, notice that one event scheduled another event with 2 scheduling edges. Normally, that's an unusual thing, but it's not an illegal thing. In this particular case, since there can only be one of these, I need to make sure that the edge conditions are mutually exclusive. So in other words, only one of these can be true. The other thing is that with respect to arguments is that the arguments are not arbitrary. They're not, you can't just kind of put I everywhere and make it work. It has to be deliberate. Okay. I don't know how much time I'm going to have for implementation, but okay. So now here's a tweak on this, and it's where we have, in addition to having different service times, I have our low priority items, or I'm actually here I'm calling them A and B just to make sure there's no confusion with the other one. So now type B required 2 servers, and they're actually the ones that I'm going to prefer. And again, all of this can be, the assumption can be examined. So the parameters are pretty much the same as before, except with slightly different labeling. We have the service times for each of the different ones. Here's one server. The number of available servers as a state. Here. And then the two different types in the queue. So now just kind of looking at our events. Again, always begin with run. I sometimes forget to, I always do it when I'm doing it. So I sometimes forget when I'm presenting it. So, but yeah, always start with run. So we can always write something down. And again, we've arrival A, okay, increment that. Arrival B, increment that. Not a problem. Okay, now A's, they just have one, they just need one server. But now, okay, so the type B's, they need two servers. So when I start service on a type B, I take away two of them. Okay, so again, this sort of decrement by one is not, that's not boilerplate. We take away one here because when we start service on a type A, we lose one server. It takes one server. But here, because we require two servers, then we take away two. Also, now can you see the implication for a model like this in terms of the constraints on the parameter, the total number of servers? So in our multiple server queue, the total number of servers needed to be bigger than 0, otherwise the thing wouldn't function. Here, what would happen if we only had one server altogether? B would never get served. So the system doesn't make any sense if we have fewer than two servers. So that would be another constraint on the parameters. So if I tried to instantiate one of these and only gave it one server, then I would say, hey, it's not going to work. So that would be a constraint you'd put on the setter for that. So now let's okay, so the B's actually, interestingly, work a little more closely to what we're used to. So just focus on this piece right here. So we see that when a B arrives, we need to make sure that there are at least two. S bigger than 1, S bigger than or equal to 2 might be more informative, but okay, so when I start service here, we take away the 2. And when we end service, because we prefer them, then we schedule them right back. And because we've gotten 2 additional servers here. Similarly, over here, because the type A's only need one server, we need to only check to see that there's one available. And just as before, we don't need to check the other because, well, if there's only one server available, then there aren't enough to serve the B's. If there's 2 available servers and B's waiting, then what the heck are they doing? Okay, so the end server, and then here, okay, so we have that. Now, this is when things get dicey. So let's look at what happened. And the here, this is this right here. So and of course all right, so under what conditions, well, when we finish service on an A, then what do we do next now? Now we have one more server than we had before. There are a number of different possibilities. So let's see under what conditions. Well, we prefer the type B's, right? So if there's a type B waiting, then we may want to be able to schedule a start service on that. But we only know that we could have one server available or we could have more. if we only have one server available, can we schedule this? No, because we need two. So if we have these guys waiting and another server in addition to the one we just got, then we can schedule the start service here. On the other hand, okay, what if that's not true? If that's not, under what condition might we schedule a start service on the unpreferred one? Well, basically, if you recall your Boolean logic, basically not this. And when we not this, when we not an and, it turns into an or and flips both of them. Okay, so not q bigger than 0 and s bigger than 1 is q equals 0 and s equal 1. Now, notice that s equal 1 is not the complete inverse of this. Why can I write s equal 1 as the opposite of this? Exactly, yeah. So I've just done a state transition where I've incremented s, and so now I have at least one. I always have at least one. So if I don't have more than one, the only other possibility is I only have one. So that's not this, and there's an a wait. Yes.
Do I need both conditions? Because if I have one in the QA, is it possible to have the free server?
So can you say that again? Yeah.
If I have one in my QA,
Yeah.
then it's not possible that I have a free server. So I don't use the first condition. Huh?
Oh, at this? You mean this condition? Well, well, the thing is that right before this event occurred, I could have customers, QA customers there, but S is 0.
Yes, that's true, but I can't have the case that I have one available server and one in the QA. It's not possible.
That's true right before this event, but after that event, it is possible. In other words, after I've added the server, yeah.
One server.
Yeah.
So, I don't have to do
Yeah, if the, well, I need this condition because if there aren't any QAs waiting, then. Oh, yeah, well,
because if I have
Yeah.
More than one available server.
yeah, I see what you're saying, yeah.
One in my QA.
Correct, yeah, you are correct, yeah. Yeah, so in other words, what you're saying is that this condition can be eliminated.
Also,
What this one?
Q is equal to 0 because if I have if my QA is greater than 0, then I don't have two
Yeah.
available server.
Correct,
Can't have.
yeah.
So, it should be enough if I only need two if QA is greater than 0.
Well, yeah, you're probably right. Yeah. Yeah, the reason for the reason for this is just sort of the total, not that, but you're probably right that this is all I would need. Yeah, good point. Yes.
My question back, people in the what's going to stop them from completely getting them in the head. But where he prefers.
Well, it comes in this edge right here. So in other words, well, with the rules as they currently are, what could happen is what you're suggesting, that as the A's keep kind of stealing the nickel and diming the servers, and the B's kind of get screwed a little bit. Yeah.
You're in the rival A and the rival B at the same time. How are you going to put the point inside two active code?
Yeah, that's where we would have to have the high priorities come in. Either one, like once you put a high priority on, then the event you're scheduling is going to happen before the other one. And so, I mean, it depends on the particular situation, but once we put the high priorities on, then, which I neglected to do for this, but nevertheless will be there. So let's say there are two servers available, and for just by chance, like one of these events is going to happen first. So if the B happens first, he's going to schedule start service with a high priority, which puts it in front of this one, even though, and then it'll yank him away, and then by the time he gets there, they're not there anymore. Yeah. Now, on the other hand, if this one happens first and there are only two of them, he's going to steal one, and then by the time this guy comes, he's going to say there's only one, so I got to wait.
So very effective if A and B that would provide.
Yeah, I mean, what I just said. In other words, one of these, when we say at exact same time, one of them is still going to happen first. And now, if they're happening, any two events that happen at exactly the same time with exactly the same priority, it's indeterminate which happens first. So it could be, so the thing to know, or the thing to kind of work out is, regardless of which one happens first, is it still going to work? Because a lot of these zero things are only because certain times are so negligible that they're, so if we're talking about service time in minutes versus time, like the time to go from the queue to the server in seconds, or when you say arrive simultaneously, well, that usually, I mean, that never literally happens in reality. Even if I had two people come in, one of them is going to get into the door first, even if it's a microsecond before the other one. Now, so in the model, for the model, it's ambiguous as far as which one it is. But it shouldn't matter, and that's where these high priority things kind of come into play. Like, in other words, if we didn't have those, then things would kind of go wonky. Okay, and I see that we're actually at time. So apologies for these. I don't know why. So okay, so before any questions from the remote folk?
Sir, I have a question on this slide, but it sounds like we're going to come back to it tomorrow, so I can ask it then.
Okay. Can you ask it then?
Yeah, I assume we'll continue to cover. If we start at this slide tomorrow, I'll ask it at the beginning of tomorrow's class.
Yeah, we'll do that.